Okay, good afternoon to everybody. This is the June session of the Young Seminar of the Italian Society of Statistical Physics. And today we will have, as usual, two speakers, Rafael Díaz and Niccolò Zagli. And the first one is Rafael Díaz, who in 2017 got a Master of Science in Physics at the National University of Mexico, working on randomness characterization through Bayesian model selection. And 2 years ago, he got a PhD in physics at Roma, at the University of Sapienza, working with Federico Ricci Tersenghi and Giorgio Parisi, and the title of the thesis was Numerical Study of the Microscopic Structure of Jammed Systems from Inferring Their Dynamics to Finite Size Scaling. And since his discussion of thesis, he has a postdoc position at Sapienza, and today Rafael is going to give a talk with the title The Jamming Transition of Hard Spheres through the lens of constrained optimization. So Rafael, you have 25 minutes, and I will warn you 5 minutes in advance, please.
Okay, thank you very much. Just can you confirm that you can see my presentation now?
Sì, possiamo vederlo.
Great, thank you very much. So, hello everyone, I am Rafael. I want to thank everyone for the opportunity to giving me this talk and to be able to participate in this very nice series of seminars. I will tell you today about a work I did with this wonderful group of people, Claudia Artiaco, she's now a postdoc in Università, and professors Giorgio Parisi and Federico Ricci Tersenghi from Sapienza. And our work consists in how we can tackle the problem of generating packings of hard spheres at the jamming point using tools from mathematical optimization. Of course, I will define all of this during my talk. I will begin by saying what is jamming, why it's interesting, and why the case of hard particles is more complicated than the case of soft particles. And then in the final part, I will describe briefly how we were able to solve this problem and some of the things we can do with it, with this approach we generated. So let me begin by saying that actually you can find many examples of jammed systems in your daily lives. For instance, what I am showing here are some grains in the left part. Grains, this is toothpaste, this is mayonnaise, this is shaving foam, this is a vinaigrette, and also in experiments of granular matter, for instance, people have tried to using M&Ms because they are very regular spheroids. That is, the way they fabricate M&Ms is a very reproducible way. And the things that all of these systems have in common is that in all of them, their degrees of freedom are blocked by some kind of frustration. For the case of my talk, what can cause the frustration are many different things, many types of interactions between particles or the agents of your model. But for the case of my talk, the most important thing will be geometric constraints, because for hard particles, what really counts is the geometry. In the case of spherical configurations, jamming is also an instance of what mathematicians call the sphere packing problem. But in that case, they're actually more concerned with the maximal density you can reach. So for instance, we know that in 3D, the solution is the FCC configuration. But to observe the interesting features that I will tell you in a second, you actually want some disorder. So it's a special instance of the sphere packing problem that should include disorder, as the panel I'm showing here in the middle. These are the so-called random closed packings, and these are the ones that will be interesting. And now, why disorder? Essentially because instead of considering a regular array, as I'm showing in the left, we want to study the type of configurations that I'm showing on the right. And it's not only that they say they look like a nice picture, it's also that physically they have interesting properties. For instance, heterogeneity that you can see visually in the panel on the right, because what I am showing there is the network of contacts, and the width of each line is proportional to the magnitude of the force. And as you can see, you have a broad range of distributions. Also, you can consider how many particles, how many neighbors each particle has. And the orange particles, for instance, they are rattlers. Essentially, they don't belong to the network of contacts. They are sort of defects. And you wouldn't find any of these in the case of the crystal, right? Also, how they respond to external perturbations, which is what I try to illustrate with the two figures in the bottom. What I am showing there is the same packing than above. It's only I removed the orange particles. And what I am showing is the displacement field that you will see if you were to open infinitesimally the contact between the particles that are highlighted in green. So as you can see, depending on which point of the system you try to perturb, you have a totally different response. And you wouldn't find this in a crystal either because of symmetry and regularity, any contact is essentially equivalent to any other. So the idea is that we want to understand these properties in systems of hard spheres. So let me begin by being a bit more precise of what constitutes a valid jam state of hard particles. And when I say hard particles, I mean infinitely rigid. So essentially, there is no interaction energy between the particles. So the first thing, of course, you have to specify is the positions and the sizes of the particles. You can think that all of them are the same size, but the argument is general if you have a distribution of sizes. So to generate a valid state, you need two very important requirements. One is that particles shouldn't overlap at any point. And this is expressing this so-called excluded volume condition that tells you that the distance between any pair of particles should be larger or equal than the sum of the radii. And then for any valid configuration of rigid particles, there are a set of 4 mechanical constraints that should be fulfilled, essentially force and torque balance, Newton's third law, and so on. But in the case of frictionless spherical particles, which is the one that I will be considering from now on, it's enough to see that the forces are parallel to the contact vectors, and then 3 out of the 4 constraints are automatically fulfilled. So only 2 important things you should consider: the excluded volume condition and the force balance per particle. And this is enough to have a valid jam state, but not to observe all the phenomenology that I was mentioning in the slide before. To do that, you also need an extra condition that is the isostaticity condition with disorder. And this happens at a very precise point called the jamming transition. So let me tell you a bit about this jamming transition. What I am showing here is the phase diagram of hard spheres in terms of the pressure and the packing fraction or density, phi. I will always use this letter for the density. And the equilibrium branch is the solid line here. So it begins with a liquid for small densities. Then you have a coexistence of the liquid and the solid. And then at some point, only the solid branch survives, and you can keep on compressing until you reach the FCC configuration. At that point, you see that the pressure diverges because you cannot pack the particles any more tightly. However, what we are interested is in this, in this extension of the liquid branch. And there are techniques to do that in simulations, but also in experiments. And if you do that, you essentially keep on the disorder of the configuration. You go through a glass phase, and eventually you will also see that there's a point where the pressure diverges, but while keeping the disorder of configuration. And that signals that you reach the jamming point. And this jamming point is important not only because of the divergence of the pressure, but because it also signals that you're in a phase transition. And I think the best way to understand this phase transition is to understand this as a rigidity transition, because this jamming density is the first point where the configuration creates a network of contacts that spans the whole system, and then it's rigid. It supports a load or a weight. If you think what happens at smaller densities, even close to the jamming transition, particles are essentially bouncing off. They will not move a lot, of course, because they are already caged by their neighbors, but they will be, let's say, vibrating around their equilibrium position. But as soon as they touch another particle, they will bounce off. They will never form a stable contact or a force binding contact. Well, as soon as you reach this critical density, at some point you have a full network of contacts that spans across the whole system. If you think what happens with soft particles, you can also approach this critical point, but in the other direction. And in the case of soft particles, what happens is that for high densities, all the particles have so many neighbors that you can think that you can remove some of the contacts, or actually some of the particles, and the configuration will remain stable. But as you decrease the density, you will reach this point where it is enough to remove a single contact, really just one contact, and that will make all the system unstable. And of course, there are some other reasons why we think this is a phase transition. So as a bona fide phase transition, there are some power law scalings with respect to the distance of the critical point. For hard spheres, as I was telling you, there is a divergence. In the case of soft spheres, the pressure actually vanishes with an exponent that depends on the type of soft particles that you are modeling. Usually it's 2, so harmonic spheres. But more importantly, what happens is there's a discontinuity in some of, let's call roughly order parameters. In this case, is the mean connectivity of the spheres. As I was telling you, before the critical density or the jamming density, it's essentially 0. And as soon as you reach the jamming density, it jumps discontinuously to a finite value that is 2D, twice the dimension. And that's a critical value because it's precisely the value you need to reach the isostaticity condition, which means that the number of contacts that your system has is exactly the number of degrees of freedom it has. So all the degrees of freedom are blocked. And this is what people observe both in simulations and in experiments. So this is, let's say, the criticality of jamming. But how do you actually generate jam packings? And even if you can understand the criticality from both the regimes, the hard sphere and the soft spheres in the same way, numerically, they belong to two very different worlds. And this is because for hard spheres, the potential is discontinuous and infinitely discontinuous, if you wish, because as soon as two particles overlap, you have an infinite energetic cost, so a forbidden configuration. And in the case of soft spheres, what people usually do is that they introduce a power law potential as a function of how much particles can overlap or deform. So in this case, it's a smooth function. And then you know that a jam packing is essentially the ground state. So as soon as you find a packing where the energy and the pressure vanishes, then that tells you that you're reaching the jamming transition. And also you can use all the techniques of energy minimization that will bring you to this minimum of the energy. I don't want to say that it is easy. I just want to say that we know the techniques that we need to use to reach this critical point. In the case of hard spheres, it's very hard, essentially because we cannot use these energy minimization algorithms. However, we can approach the jamming point as much as you want, essentially by adding a bit of compression to the molecular dynamics algorithms that are available. This is an efficient algorithm to approach the jamming density because the dynamics is easy. Essentially, particles move ballistically until they collide, then they bounce off and keep on colliding. And this allows you to increase the pressure, but not to reach the point where it diverges. Essentially, because as I was telling you, since this algorithm works using the dynamics, the probability that you will have an event where once two particles touch, all of the other neighbors also touch, and you have an extensive network is essentially 0. You will never find this condition. So reaching the critical point from the point of view of hard particles is very hard. What people have been doing is to, let's say, build a bridge between these two worlds, is to use effective interactions. The most common one is using a logarithmic potential, because this takes into account the fact that if two particles were to overlap, it will have an infinite energetic cost. And this approach works to generate stable packings. However, we think that this is not really modeling the physics of hard spheres properly near the jamming point, right? Because, I mean, hard spheres don't see each other until they don't touch. If they don't collide, they don't see their neighbor. So introducing this type of interactions is a bit fictitious. And also because what determines the properties or the thermodynamics of hard spheres is the entropy. Well, when you introduce a potential and you want to look for a minimum, you're essentially looking for the ground state of the energy. So you're using the incorrect thermodynamic potential. And this will be important for a thing that I will tell you in a second. Next, I will try to answer a question that probably many of you are already asking, like, if everything works so well with soft spheres, why do we care about the hard particles? And there are a set of important reasons. One is, for instance, that granular matter can only be modeled using hard particles, or at least is the best approximation. But what really motivated us is to test the hypothesis of a mean field theory of the glass and the jamming transition. It's a theory that is exact in infinite dimensions. And I'm sorry, I don't have to go into the details of the theory, but I will give you two important predictions of this theory. One is about the critical distributions of forces and gaps. And what does this mean is that imagine that your best friend gives you a packing, and then they ask you to go and measure the distance between the borders of the particles. And your friend tells you, well, there is this very nice theory that says that if you go and make a histogram of this distance between the borders of the particles, you normalize everything by the radii, so to make everything dimensionless. And mean field theory predicts that if you do so, you will find this power law with this strange exponent. And you can actually see that this is the correct power law even before you reach the jamming point. So it's not really mandatory to reach the jamming point to see that this is the right power law. However, your friend will tell you that there is something else that the mean field theory predicts, and it is about the distribution of forces. So you take the same packing, you measure the magnitude of contact forces, and once again, it should have a power law behavior with this exponent. And then you ask around your friends, does anyone have any data? And well, if these people give you the data, they told you, well, we make simulations in 2, 3, and 4 dimensions, and we found an excellent agreement. And what I mean by excellent agreement is that you should be comparing the triangles in each plot with the red line. The red line is the theoretical prediction, use the cumulative distribution, but that's just a technical detail to make everything a bit more accurate. And they find a very good agreement. So then it's a very good situation. However, these simulations were done using soft spheres because, as I was telling you, we know how to handle soft spheres. So this is, we wanted to test if we can do the same with hard particles. And the other thing we wanted to test is another prediction of mean field theory that concerns the structure of the free energy landscape. Essentially, the theory tells you that any jam configuration, any packing corresponds to a minimum of the free energy surface that is a high dimensional and highly non-convex surface. And it has a peculiar structure, but the basic idea is that 2 nearby minima will correspond to 2 different realizations of network contacts or of jam packings. And the general structure of these network contacts will be the same, but the specific details, the fine details, which particles are really in contact with which one, would differ from one configuration to the other. And people have done numerical experiments to test this, and it works very well. Here, what I am showing is the similarity between network contacts as you go down in the energy landscape, but not as you reach the minimum. So what they did was to make a time average of the list of particles, or list of neighbors a particle had during the molecular dynamic simulations, and they saw that as you increase the pressure, the list of neighbors become more and more similar. So I don't want to be dismissive. These are already very good results that tells you that probably this is the right picture, but since they don't have enough resolution to distinguish the network contacts at the minima, then maybe, I mean, we can do better if we were able to explore the real minima, right? So, I'm sorry, and here it's a good point to tell you that this is also a good reason why we wanted to avoid the introduction of any potentials, because you want to sample the right free energy, and for hard spheres, the right free energy comes from the entropy. And when you introduce a potential and you go to the zero temperature limit, what you're actually sampling is just the entropy or the Hamiltonian. So if we want to explore the structure of the landscape, we have to make sure that we are probing the right thermodynamic potential. So that's also what motivated us to tackle this problem. And the way we do it is by implementing what we call the Calypso algorithm. With this algorithm, we are able to generate these sort of packings, as the one I'm showing in the figure, where the color code corresponds to the number of neighbors of the particles. The dark ones have no force binding contacts, and the light particles have as much as 10 contacts, I think. And some features of this algorithm is that we didn't need to include any interaction potential at any point, and we didn't have any overlaps, of course. And the way it works is because it exploits the geometrical constraints of the problem. And that's why we also think that in some way, what drives this algorithm is more the entropy. So we think that it allows us to better explore the free energy landscape. And the way it works is by solving a non-convex optimization problem that I will define in a second through a series of easier linear problems. Those are the ones that, let's say, we know how to solve easily. And the idea is the following. Imagine, once again, your best friend gives you a valid configuration of hard spheres. So they give you the positions of the particles, the sizes or the radii of each of them, and of course you are below the jamming density. And then they ask you if you're able to find the displacements or rearrangements of the particle or the configuration that I will denote by S, such that when you transform the configuration by such displacement, you're able, with this new configuration, to maximize the density, to inflate the particles as much as possible. And of course, without having any overlaps. Maximizing the density is equivalent to maximizing the size of the particles, because phi is only a function of how big your particles are, right? So this idea of maximizing the density can be translated into an idea of maximizing the particle's diameter, which I will express in this way using an inflation factor gamma. So I want to scale all the diameters by the same factor, and I will tell you why I'm using a square root here in a second. But then the idea is that mathematically, this is the optimization problem you have to solve. Maximize the inflation factor, and then add a non-overlapping constraint for each pair of particles that takes into account that particle will be displaced and they will be inflated. If you're able to solve this problem, you make this transformation, and that's it. You've solved the jamming problem. However, of course, this is not so easy, essentially because this is a non-convex problem, because the constraints, the non-overlapping constraints, induces holes in the sets of solutions, in the space of solutions, sorry. And this is what I am trying to illustrate here. The set of solutions is the gray area, and each non-overlapping constraint is this white donut. It's a forbidden region with respect to the center of the black particle. So the center cannot go into that region, otherwise you'll have an overlap. And this fact that you have holes is what makes the problem very, very hard to solve. So the idea Giorgio had was to let's say, okay, what happens if you're not at jamming, but very close to jamming? If that is the case, then the typical displacements will be much smaller than the typical distance between particles, right? Which means that we can neglect the second order terms of the constraints, and we end up with this linear optimization problem. That is why I was using the square root, because both the constraints and the objective are linear. And graphically, that means that instead of considering the donuts, we just have to consider these straight lines as constraints, and now the space of solution is a polygon, or in higher dimensions, a polytope. But polytopes are always convex, and we know how to solve convex problems, especially if they are linear. Like, I'm sure if you go and choose your favorite optimizer, it will have a linear solver. So we can solve this problem. But by itself, this is not enough. Essentially because the optimum of the linear problem will not be the optimum of the exact problem. And this is what I am trying to illustrate here. The optimal solution is at the intersection of the linear constraints. That is a general feature of linear problems, which is the red star here. And as you can see, that intersection doesn't match the intersection of the exact ones, which are the dashed lines. However, there is an important thing to notice here, and it is the fact that the polygon or the polytope is always contained in the original set of possible solutions. That means that even though I just find an approximated solution, this solution will not have any overlaps at all. And it also allows me to make the particles a bit larger, right?
Rafael, hai 5 minuti.
Okay. Yeah, I'm about to be finished. And the idea is that since we have these properties, we can use the same transformation we had planned before, and we will have another configuration without any overlaps and with a larger density, which means that we are already closer to the jamming point, and we can use this new configuration as a new initial condition for a new instance of the linear problem. And then we essentially iterate this process of using the solution of the linear problem to generate a new initial condition. And visually, it means that at each step, instead of looking for solutions in the gray area, we only look for the solutions in the pink region here. And as we iterate, the linear approximation every time is a better approximation of the exact space. But more importantly, the space of solution shrinks. And at convergence, it shrinks into a single point. And the solution at that point is that the optimal displacements are 0, so no displacement, and the optimal inflation factor is 1, so no inflation. This means that I have effectively blocked all the degrees of freedom of the system, right? I cannot move the particles, and I cannot increase the density. And this is essentially the idea of how our algorithm works. And with this approach, we can generate this type of packings. And okay, let's say this is the intuition, but you can also make a more rigorous analysis. For instance, we were able to show that there is a one-to-one correspondence between the forces and the Lagrange multipliers of the linear constraint. And once you solve the problem, you also have access to these Lagrange multipliers. So then you also have access to the process, and you can extract the full network of contacts in a single run. And more importantly, using some theorems of optimization theory, especially the Karushkin-Tucker conditions, we were able to show also that at convergence, our algorithm will always satisfy the mechanical equilibrium for each particle, and also it always gives isostatic packings. But the isostaticity is fulfilled also including terms of order 1/n. So it's a very precise algorithm. And now that we have this algorithm, what can we do with that? Well, in this collaboration with this very nice group of people, what we did was to make a comparison of the critical exponents of the force distributions and the critical gaps distribution, but now using data from soft spheres and from hard spheres. And as far as I know, this was the first time that the data of hard spheres had the quality enough to make a direct comparison. And here you will tell me, but there are strong deviations from the theory, which is the red dashed line. And yeah, but we were able to show that these deviations come from finite size effects. We were able to derive the correct scaling function to correct for these size effects, and that is how we found that the mean field theory predicts the right exponents, and there's essentially a perfect matching between the two sets of data. So essentially, this means that it doesn't matter from which direction you approach the jamming point, you will always observe the same critical exponents. And finally, now that we have a more precise algorithm, we can improve on the accuracy on how we can explore the structure of the free energy landscape. So this is the same picture I showed you before, but now this is the results with our algorithm. This Q is the measure of similarity I am using. It's essentially the fraction of contacts in common that you have between two different networks. And as you can see, we have precisions of the order 10 to the minus 4 and 10 to the minus 5. So it's a very precise. Actually, for the smallest system, the gray curve here, the last point, this corresponds to be able to distinguish a single contact, difference between two networks, which means that, I mean, you cannot do better than that, right? And this is what our algorithms allow us to do now. And finally, a slide of publicity. We also make a Julia implementation of our algorithm that you can download for free, of course, as any other Julia package. It's called calypso.jl. And what I am showing here is how many lines of code you need to generate a packing from scratch. Essentially, you load the package, you choose your solver, there are many available, and this will generate a jam configuration of 500 particles in 3 dimensions. This generates a configuration from scratch, but of course, if you have your own, you can use that too. And the magic comes from calling one single function, which is this one, that essentially implements the chain of linear optimization problems until it reaches convergence. And when you call that function, you only have to wait a bit. And they'll, like, I swear to you that I didn't do anything else. This was the output. And it tells you that after 158 instances of solving 158 instances, it converged. As you can see, it automatically checks for balance. If it's not fulfilled within an accuracy of 10 to the minus 12, it makes an extra linear optimization to fine-tune the Lagrange multipliers and reach much better accuracy. It's going to be isostatic because that, as I was telling you, that's part of how our algorithm works. And I think that's it. You can find more details in this work, or if you want to download our package, it's available in this GitHub repo. Thank you very much.
Thank you very much, Rafael. Thank you very much. So, are there questions or comments? If not, I have one.
Yeah, please.
With respect, it is a very general and very basic question.
No, please.
I mean, with respect to the jamming transition, soft particle and hard particles belong to two different universality classes.
No.
Oh, okay.
They actually, that's the idea of our. I mean, if you care about the critical properties of the forces and gaps distributions, they belong to the same universality class, which is what we try to show in this work, that they will exhibit the same critical exponents. If you consider what happens in the vicinity of the jamming transition, these scalings have different exponents, but there is a scaling function that can capture both of them at the same time. So I would say they belong to the same universality class.
Okay.
May I ask a question?
Yeah, sure.
I'm wondering whether the results, because it's a very algorithmic driven problem, this one, could be somewhat dependent on the algorithm that you choose. So,
okay,
let's say I have a simpler, worse algorithm, I find the worse results, or let's say different ones. How do I compare them with yours and so on?
Thank you. That is a very good question. So I think there are two things to consider here. One is when I give you the optimization problem, how you choose to solve that optimization problem can lead you to a different solution. If you try to use a linear approximation or any approximation that will make that problem convex, as much as the solution to that convex problem is unique, as it's usually the case for complex problems, then you will essentially end up with the same solution than we did, up to machine precision, of course. So yeah, then that's a different topic. If you were to use a different approach, not without the geometrical constraints, then it can lead to different configurations. I would say in general, probably yes. But what I tried with some of our colleagues is I gave them one of my hard spheres configurations. They introduced a bit of overlaps and an interaction potential to make them soft spheres. They went back to the jamming point and they obtained the same configuration, exactly the same position. Everything was the same.
Okay, thank you.
Thank you.
Any other comment? Okay, if not, let's thank Rafael again.
Thank you.
And